So in this example, we're going to do something slightly different. In the previous four, we looked at a specific affine mapping, and we tried to determine what happened to a geometric object under that affine mapping. In this case, we are going to actually try to find an affine mapping that does a specified thing. So in particular, what we want to do is we want to take a triangle. Our starting triangle T is going to have vertices 1 plus I, 2 plus I, and 1 plus root 3 over 2I. So if we were to graph those points, looks like we need to go out. I'm going to go out a little bit. Let's go out 3 in either direction. And here in maybe blue, we'll say where we want to start with. So we're going to start with 1 plus I, 2 plus I, and then 1 plus I. Oops, no, this is not quite right, sorry. This is supposed to be, oops. The vertices I wrote down were not the vertices of an equilateral triangle. We want 3 halves plus 1 plus root 3 over 2I. There we go. Okay, so 3 halves is 1.5, and then we have to go up not quite 1, but enough to get an equilateral triangle here. Okay, so here's our starting. This is our T. That's what we want to start with. And then our T prime, I'll draw in maybe purple. And T prime, or the image triangle, we want to have vertices I, root 3 plus 2I, and 3I. So I, maybe not in purple because the axes are purple, maybe green. So I is here, 3I is here, and then root 3 plus 2I is going to be about here. So here's our T prime. Okay, great. So what we want to do is find a mapping that takes T to T prime. One of the things that we can do to solve this problem is try to first normalize T. That is, so we can kind of see here that one thing that we might want to do is rotate T in by, I don't know, pi over 4, so that it's on the so that this side here is on the y-axis, and then once it's on the y-axis, what we can do is then try to stretch appropriately and whatnot. That's all. It's all fine and good, but when we do that, it's going to be kind of unclear if it aligns perfectly, what the dilation factor should be, and so on. So I don't want to do that. What we're first going to do is we're going to translate T to the origin. And by that I mean so that a vertex is at the origin. Now, one way in which we can translate is to translate, let's call, so my choice for the names were bad. Let's use what the book's using here. So let's call this S prime, and let's call this S and S. That way I can use T's for translations. All right, so we first, for example, might want to take this point 1 plus I and subtract it. So what that's going to do is it's going to take this shape and move it so that it's about there. So that's T1 of S. So we can certainly do that. And then this angle is again pi over 4. Is it pi over 4? No, it's not pi over 4. It is, let's see. Oof. Okay, so when we do this, what happens to this upper point? Where does that go? And that'll tell us what that angle is. So let's see. T1 of 3 halves plus 1 plus root 3 over 2I is going to be subtract 1 from the real part, subtract 1 from the imaginary part. So let's see here. If I subtract 1 from the real part, I have a half, and the 1 from the imaginary part, I'll get rid of that, root 3 over 2. Okay, this is an angle of pi over 6. Sorry, pi over 6. And then what can we do? Well, we can rotate so this side is vertical. And if we do that, that's going to correspond to a rotation of we have to finish, sorry, pi over 6, pi over 3, my bad, pi over 3. How do we get from pi over 3 to pi half, so that's a full 90 degrees? We want to rotate by pi 6. Right, so now we're going to do r of, now we're going to do r of z. I think we're only going to need one rotation. We're about done. To be rotation by pi over 6. And remember, with complex numbers, rotations are simple. You just multiply by e to the I and then the angle. Okay, so now what we have, let's get rid of this intermediate shape. Now what we have is the following. We have this shape, which is first translate and then rotate. And now this side is supposed to eventually match that side, but this side is off by, well, it's double the length, right? So I think what we're going to have to do now is we're going to have to dilate by 2. Okay, so if we dilate by 2, what's going to happen is that is going to stretch everything out by 2. So this is d of r of t1 of z. And then lastly, we need to translate everything up by I so that it aligns. Translate by I. So this is our second translation. We're going to do z plus I. Now, again, our actual mapping, the one that takes S to S prime, is to do these in order. So once we do these in order, we will get the corresponding shape. So T2 composed D, composed R, composed T1, all on S is that green shape. But we don't know what the mapping is. We actually have to do the composition now. So let's do that. Let's compose them and see what we get. So T2 of D of R of T1 of Z is going to be T2 of D of R of T1 is the subtract 1 plus I from me function. And that's going to be T2 of D of R is the multiply by e to the I pi over 6 function. Okay, and we'll worry about what that is. Well, in a second we'll worry about what that is. D is the multiply by 2 function. And then finally, T2 is the add I function. Now, this isn't quite written as an affine mapping just yet. So we'll get 2 e to the I pi over 6 z minus 2 e to the I pi over 6 times 1 plus I. And e to the I pi over 6, I'm going to leave that first part alone, but we can to make the second part look a little bit better, we could rewrite this, of course, as root 3 over 2 plus 1 half I times 1 plus I. And I'm not going to do the arithmetic, but if you were to do the arithmetic, what you should find is you're going to get plus 1 minus root 3 as the real part, and root 3i as the imaginary part.